Gravitation is one of the fundamental forces in which it almost governs everything that we do around the universe here, from the orbit of the moon, from us orbiting the sun. And so the main focus is to try to explain what is the tidal force, but we will need to build our understanding of the gravitation first. So before we get started into the video, make sure to like and subscribe, and also please check the notes in the description for the notes throughout this entire discussion, as well as the timestamps below for you to skip through just in case if you want to understand only a certain part of the entire video. So let's introduce ourselves to gravitation. So Newton's law of universal gravity states that the gravitational force is proportional to the masses multiplied, also the r squared, the distance squared, in the direction of where the object is. So like so, but the question is, does it go inwards or outwards? And it turns out that we could actually figure out, actually we could just see that this thing would have a negative at the front. And this is our constant. So this constant here is 6.673 times 10 to the power negative 11. Technically there's a plus minus 0.01 here. And the units here, if you actually look at the formula, it should be Newton meters squared per kilogram squared. And so this is only for one object. And so if you want to figure out what's the force for a continuous object, instead, let's actually consider if you have two particles. And you are interested in this third particle here, m1 and m2. And this is m. So there will be a force of gravity coming from m1 and also from m2. And it turns out that the gravitational force is additive, so you could just add them both up. So it could be written that the force vector is the sum of negative g of the m times the mi over r squared r hat. And so if we observe this, sorry, this is ri and ri hat. And so if we actually try to rearrange this, this is negative gm sum of I of mi over ri squared ri hat. Now this is only for discrete, and so if you want to make this into continuous, you'll just turn the m into rho dv. Technically this is dm, and so it would become negative gm integral of the volume of the rho dv in each of the r hat directions, r hat, divide that by the r squared. So don't forget that this dv and this r hat here are actually different coordinates, just to make sure. And so this is why I put a prime at the top. Now, because if we see here that this thing here is actually proportional to the mass here. And so this is one of the properties of the interested particle. And so if we can remove such parameters, it would be better for us. And so we could do that. We could just try to define what's the F vector over m. And this is what we call as the gravitational field. And so the gravitational field, the unit is acceleration. It's negative g, the integral of the volume of rho r hat, rho r hat dv prime over r squared. Or if it is only a singular particle, you could write this as negative g m. Well, technically it's the big M. That's the one that it's sourcing from. Negative gm over r squared, r hat, like so. So what this gravitational field exactly is that this is a mapping of the entire space in which if you have a particle of mass m, it would have force to be equaling mg vector. That's the elegance of the vector field. It's very similar to the electric field in which instead it's charge, or magnetic field in which it's charge as well as the velocity. That is going to be determining what's the force on the object. So this formula here could be used to compute the gravitational force near the Earth's surface. And so you could obviously do that, but in here I'll just show you that if you plug in all the values, the g vector would be 9.8 meter per second squared. So this is basically the constant that we always use when we did parabolic motion in terms of the Earth. It's normally 9.8. Or in engineering, sometimes you could also use 10 meter per second squared. It really depends. So something that I want to note from our vector calculus is that you could try to figure out what's the curl of the g vector. And if you try to analyze this only only from a singular particle, you would straightaway see that this is 0. And if you actually do this for the continuous as well, if you try to think hard enough, like doing each of the particle one by one, and figuring out that each of the curl is 0, combining them together should also produce a curl of 0. Thus, if this is the case, you could always define the g vector to be some form of gradient of a function, and it's much more convenient for us to write that as the negative. And this is what we call as the gravitational potential. So trying to solve this for a singular particle, you could just stare at it, and you could figure out that actually this function is defined to be negative gm over r. And if you try to think of this in terms of multiple different particles or in continuous media, it's just negative g integral of rho dv prime over r. And you could also technically define for the surface and for the linear, but in here, this should be sufficient because anyways, if you are dealing with, let's say, surface density, like instead, this will be just the d surface instead. So it's quite simple for you to transform between from the different components of the gravitation. And so what is the use of the gravitational potential? So in order to see the use, we need to try to examine the energy. So let's say if you have one particle and another particle, and there's a gravitational field. And so what's the use of the gravitational potential? In order to realize this, you just need to analyze that actually, if you see here that this is actually the gradient of f vector over m is equal to 0, where m doesn't really change across the space. Now, just pull the m outside, and I mean technically multiply both sides by m, you would get the curl of the f vector is 0. This means that this is a conservative field, a conservative force, technically. This means that there should be a value that we could denote such that it can define what the force is. And if you remember previously, this is something which we call as the that's the potential energy. So notice here that this f vector is negative gradient of u, but this is also mg vector, or it's negative m gradient of phi. Now you see here that u is m phi. And this is basically the relationship between the potential energy as well as the gravitational potential energy. It only has this dependence in m. This is like the energy for, let's say, the electric field. So let's try to develop the Maxwell's equation for gravity. The way we do so is to define the flux n dot g dA. And if you do the actual experimental value here for the g, it's gonna be negative g times the mass cosine theta over r squared. And so you could integrate this over the surface dA. And something to note is that you could actually try to evaluate this, and this turns out to be the integral of the solid angle, technically. And this would give you the value of 4 pi, which I would prove here, but you could actually see it somewhere, or the definition of this, the radians. But anyways, you'll see this 4 pi on the right-hand side. And on the left-hand side, you could use some ideas from vector calculus. So on the left-hand side, it's just mathematics. So g dot n, that's basically, if you take the volume integral, technically this is a closed surface. So this would become the volume integral of the divergence of g dv. This would equal to negative 4 pi g m. Now, if you convert this mass into the continuous formula, it's the integral of the volume rho dv. And so if you group them all together, you could get that the divergence of g is negative 4 pi g of rho. This is the Maxwell's equation for gravity. And thus, because you know gravity is negative gradient of the scalar potential, no, sorry, the vector potential, the gravitational potential, my bad, it would become the Laplacian of the scalar potential to be equal to 4 pi g times the rho. Now, this is the Poisson's equation in which you could solve it's very similar to the one in the electromagnetism. A very special case is when rho is 0. So it's just Laplacian of phi is 0. And this is what we call as the Laplacian, Laplace's equation. And so something that I want to note is that to solve Poisson's equation, it's much more ideal for you to use the Green's function method, and then you just add in the Laplace's equation into the formula as well. No, sorry, into the solution as well. So now I want to show you some ways for you to draw the gravity field, the force, and etc. So one way to do so is by using the lines of forces, lines of force. So the way that it works is that let's say you have, let's say you have this object here, and you want to figure out what's the force direction. So the way that you could do that is that you could figure out the the gravitational field at a certain point and just draw the vector. And it turns out that this would actually be collected into one single vector. This is what we call the lines of force. And this just shows like where does the force go? In here it is always attractive. And so visualizing this is that if the arrows get much more denser, let's say near here, this means that it has a higher force compared to a very sparsely distanced here. The density is very small. So this would be much more smaller. You could also use the potential idea. So if you have, let's say, the same mass and you're using potential, you could you could just define the potential to be constant for a certain function. A so this function technically only has n minus 1 independent variable, as the last one is dependent on the other two, because this thing here is constant. So it would basically show what is the value of the gravitational potential. So it turns out that this entire ring here, it has the same gravitational potential, and in here, same, and then going outwards. Technically, this should go with a distance of like 1 over r, because ideally it should be like the change between the scalar potential should be constant, but it's fine if you don't actually do it that way. But still, it's much more ideal for you to draw it with a much more constant difference. So you could actually convert from one visualization to the other. And so for the lines of forces, you could actually just draw a surface that is tangential to all surfaces, like so. And for the gravitational potential picture, you could just draw vectors that is always tangential to the surfaces. This would just show you the lines, but not really the direction. And so the way that you determine the direction is simply just by denoting what the value is. Let's say negative 0.8, negative 0.5, and negative 0.2. So you would see that the force would want to go much more nearer. So this is the equipotential surface. So some people might be asking, like, why do we use the gravitational potential since most of the information is from the gravitational field? And the answer is actually both of them give you the same amount of information. But the difference is that one of them plays with vectors. So if you do, let's say, let's do the negative g with the integral of m, and we multiply that by r hat, divide that by r squared, you see that there is, sorry, there should be, technically this is rho. Let's use rho. So it's rho dv of this guy here. Now something to note here is that we have a vector here. Now this would mean that there would be three different functions, like there would be three different equations for you to solve. One in x, one in y, and one in z. So it has a much more cluster of the function. And same thing if you just do the divergence of g equaling negative 4 pi g rho. And technically these two are basically the same thing. And so this would require you to solve the x, y, and z, but in different ways. And this is much more harder for us to solve because we need three different equations and sometimes we don't know how to solve it for like the differential form. But if you actually try to, actually in here there is like another criteria where the divergence of g is 0. But if we try to use the gravitational potential, this is negative g integral of rho over r dv, you could see how simple it is. It's there's no vectors anymore. You only need to care about what's the volume density, and this is already just one equation straight away. And this one equation, it's you could also do it with the Laplacian. Laplacian of phi is negative 4 pi g rho, and this is much more solvable. This is a partial differential equation. And here it's technically a ODE. No, sorry, it's a partial differential equation as well. But instead, you need to consider gx, gy, and gz. On here, you only need to care about phi and its xyz, which is much more easier for us to solve. So now I want to discuss the main topic of this entire video. It's discussing about the ocean tides. So people used to think that ocean tides happen because the moon is pulling the water. That's partially true, but it doesn't explain why we have two tides instead of only one. Because if you think of it like so, if we have the moon here, the water should be pulled up like this only, but not from the other side. So how do we understand that there is two different tides separated by half the phase? The answer actually relies on what inertial frame are we talking about. So this discussion, we'll just do this together. So we'll just take a point in the universe where it is always stationary. It will be our reference frame. It doesn't have any acceleration. So the one that is experiencing the force are these two guys attracted by each other. And also there's like this small probe that we're analyzing. So we first try to figure out what's the force on this probe. Well, the force on the probe is quite simple. You could try to get, you can just define this thing to be the d vector, and the distance from here to here to be the r vector. And from here to here, we'll call this to be the small r vector, has mass on each. So we can ask, like, what's the force on this guy? So on the probe, it will be, it's m, and this distance here, we'll call this to be rm, r, the location of object m. So m times r double dot of m, this is Newton's law. This would equal to negative g, the mass of the moon, multiply that by the mass of the object, divided by r squared in the r hat direction, and also negative g, the mass of the earth, and the mass divided by r squared of the location of this r vector, sorry, of this r, no wait, yeah, the bottom side should be r squared, the small r squared, like so. So that's one thing. So what about the force on the earth? So we could try to figure that out. We'll just define this position to be RE. So MRE double dot vector is gonna be negative G, mass of the moon and the mass of the earth, divided by d squared in the d hat direction. Subtract this by, well, yeah, we can subtract this by G mass of the Earth times the mass of the small object divided by r squared in the negative r hat direction. Something that I want to note here. You could compare these two values. The mass of our object is very small compared to the mass of the moon. So therefore, we could just ignore this. And thus, we have these two different equations. Now, the thing is that we don't really measure the ocean tide from outer space. We measure it from the Earth. Technically, the height from the average value, the average height of the Earth added with the water. Like that's how we measure it. So we need to change our reference frame. So we'll be changing our reference frame from this from this r moon and the re into this r vector. That's how we define our position in the Earth. So r vector is, if we do the vector calculus, it's r vector m minus re vector. And you could take the double derivative of each because it's linear, right? You could do the r double vector. This is going to be the r moon, right? So it's negative g mass of the moon over r squared in the r hat. Subtract this by g mass of the Earth over r squared in the r hat. And also we have, for the one on the moon, it's going to be positive g, the mass of the, sorry, this is the mass of the Earth. So it's the mass of the moon divided by d squared and the d hat. And so if we try to group each of these, we can see that this is actually the force because of the Earth. So if you try to think of it, if you have a body of water in an Earth, the obvious answer is that it won't be moving even though if you are jiggling it around. I mean, technically, if there's no forces from the outside, it would move at constant velocity. And the only thing that it would do is probably spin, in which we don't care about this at this point. So this couldn't be the source of the tidal force. So this is just basically gravitational force. Gravitational. But the other two is something which we call as the tidal force. So it's negative g big M over M, r vector over r cubed minus d vector over d cubed. Notice that I changed the notation a bit. So this and this will contribute to the tidal force. So that's Ft. And this would be a negative g mass of M times the mass of the object because it's force. This is just the r dot vector. And the components are just r hat over r squared minus d hat over d squared. Now we can try to compute this into our simulation, in which I've shown here that you could see that there is some parts that is bulging outwards, sorry, the force going outwards, some are the forces pointing inwards. So it turns out that this is not a conservative force, and therefore I couldn't really draw the potential because we cannot define the potential in here. And so this is a very subtle idea that is like breaking your mind, because gravity should be conservative. It should be a conservative force. But somehow in here, we lose this conservative force. So why? The answer actually comes from our inertial frame. We thought that ourselves are not moving. And this idea of perspective in here creates such frictional force such that we don't observe the tidal force to be conservative. Technically, if you sum up the conservative force as well as the gravitational force from the Earth, it will be conservative. But if you take out only that gravitational part from the Earth, you would see that it would be non-conservative. It's a very interesting thing to point out. So we only have written what's the tidal force. Maybe we can try to analyze some certain points. So if we have the Earth here, and let's consider these 4 points, since these are technically the extremes that we have already seen from our simulation. So first, let's consider the one in here. So we can see that there is the r hat that's going in this direction. R hat is going from here to here. The vector goes from here to here, right? So we can try to compute each of these, right? So let's just use theta instead. So it's So it's 0, pi over 2, pi, and negative pi over 2. Let's do it like so. So at 0, we can try to plot the values in negative gm m, and this r vector over r squared and d hat over d squared. It will just become, in here, r hat and d hat is in the same direction, x hat. So it's like the tidal force in the x direction at 0. And if you try to plug it in, it's 1 over r squared. R squared is, so it's from here to here. So it's gonna be d minus r. Subtract that by 1 over d squared, h of d squared. So we can try to simplify this further, like we can actually get the d squared out, negative gmm over d squared here. And so inside it will be 1 minus r over d squared, subtract this by 1. And if you know about the Taylor series, you would know that you could just expand this. This is 1 plus 2r over d if I do this properly. And subtract that by 1, this would be 2r over d. Therefore, the force in here is proportional to 2r over d cubed. I mean, like, there would be like a constant at the front. We'll just write this to be big C. So you would see that the force here is 2r over d cubed times this constant, where this constant is just gmm. There, gmm and m. And let's also try to consider the one on the right, because it's quite symmetrical. And you could observe that it will just change this value into 1 over d plus r squared minus 1 over d squared. You can do the same thing. It would give you 1 minus 2r over d, and subtract this by 1. It would give you another one, which is c2r over d cubed, but in the opposite direction. Exactly what we see from our simulation. We should also try to consider the one at the pi over 2 and negative pi over 2, but the computation is much more harder. So, if we try to think about the f vector here, f vector at pi over 2, and technically at negative pi over 2, it should be symmetrical because we can just flip it around. This would be negative g, mass of the moon, times the mass of the object that we are interested in, and the radius. The radius is much more harder, but we can figure that out to be d squared plus r squared, and then subtract this by 1 minus d squared, like so. I need to denote where the direction is. So this is x hat, and in the y hat, we cannot really use it. So instead, we'll just use 3 over 2 dx hat plus ry hat, like so. So looking at this, we would notice that this d squared and r squared here, r squared is very small compared to d squared. So we can just cancel this out. So this would be simplified further into x hat plus r over dy hat. Divide this by d squared minus x hat over d squared. And this front side would cancel out. So this would become r over d cubed. So it turns out that in the y direction, it's r over d cubed. And it's pointing inwards. It's negative. So it's constant r over d cubed. Same thing on the other side. It's a force coming inwards, like so. So we can actually try to generalize this into any type of point. So because these scales in here are quite large, we could just substitute for the ftx is 2gm times the big mass m, x over d cubed. And this x here is relative from the Earth. And in the y direction, it could be negative g m times big mass of m, y over d cubed. Now this is in Cartesian coordinates. We can do this into a polar coordinate, but the force is still in x and y. We can still do that. And the tx would just become 2g m, mass of m, the mass of the moon, r cosine theta over d cubed. And for the y, it's the same thing with r sine theta, negative. There we go. So this is only the effect from the moon. You could also try to consider the effect of the sun and try to add it up. Like there would be much more extra forces. And so this would give you the idea of what a spring tide is. And so if you see this in nature, you would see that the tides would have a local maxima over the year, and this is during the spring. So in the spring, it would have build up from the sun as well as the moon. So therefore, like the tidal force would become much more stronger. Compare that if you are distributing it across the different days. And also, technically, the tidal force from the sun is much more weaker compared to the one in the moon, because the distance here is much more greater. This is like going in the d cubed. So the closer you are, tidal force goes up quite high. Compare that with the mass, which is just linearly proportional. But still, we cannot explain fully in detail because we haven't considered rotational motion. We didn't consider this, and if we try to consider this, this would mean that each of your water would have a angular momentum. So instead, what would happen is that your tide would be shifted slightly to one side. And that's one thing. The other thing is that because the moon is also revolving, this would mean that the tide is like also trying to catch up as well. So the distance between the two tides is not exactly 180-degree phase, but there's like this small phase difference, you could say, that is contributing from the rotation of the moon as well, the orbit of the moon. So this is not a perfect model, but it explains the phenomena quite well. And so this is what we physicists do. We try to explain things that we don't know or something that is quite supernatural or quite weird. And so anyways, that's all for today's video about gravity. And so make sure to like and subscribe and also share this to your friends who wants to understand physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.